This is Precalculus, technically AP Precalculus this year. Homework 1-1, we are doing continuity. I am your host, Mr. Sindel, and I'm going to be going through the homework. All right, in this first function, again, we're not paying too much to the equations in the first half. That's going to be more of the second half. But if you want to see how these relate to what's going on here, that will help in the second half. Notice that we have a not equal to and equal to, which means we are going to have a removable discontinuity where a point jumps out. And let me make sure I'm reading the instructions correctly. We have to figure out if it's continuous at the x values, and if not, we're going to classify the discontinuity. So this is clearly discontinuous because continuity is defined as holding down your pencil, and then you have to let go, and then come down here, and then pick back up your pencil, which means we're not continuous. And what of the three types do we have? This is going to be a removable discontinuity. So I'm just going to be lazy here and say removable. And number two, notice we have kind of the same thing, where these are kind of, it seems like it's a removable discontinuity. The problem is when we plug in -5 into these x's, we get a height of 1. It should have been a height of 1, but it says, oh no, I chose -3. In this case, if you plug in -3 into these x's, you get a height of -2, which matches the -2. So because these two heights match, it is actually continuous everywhere, and this one is continuous. Or you can just do the graphical interpretation and be like, look, I never had to pick up my pencil, right? So there's another way of doing that one. In number 3, you definitely have to pick up your pencil. Look, you come up here, pick it up, and then come down here. And how do you know that it's that? Just by the equation, you can say, if you set the bottom equal to 0, then you will get -2 is a bad spot. So that is going to be an infinite. Infinite. I can spell infinite discontinuity. Number 4, kind of the same thing. You have things in the bottom. If you set it equal to 0, you get this factor of x plus 4 and x plus 4 in the denominator, which means we have at -4, that'll make the bottom 0, which is a bad value, and therefore we have another infinite discontinuity. I can say these words, I promise. And the general idea is after you cancel everything out, there's nothing to cancel. There's not. If I had an x plus 4 here, I could have canceled things out, and I would have had a debate if it's infinite or removable discontinuity. By the way, infinite always wins. It's infinitely more powerful. Haha. You could tell just by things canceling out, but we have nothing to cancel out. Therefore, the leftovers are the infinite discontinuities. And number 5. Again, it looks like it's going to be another infinite discontinuity, but you will have something that cancels out. You'll have, if you look up here, you'll have x times x plus 4, which means you'll cancel out this x and this x. So we have at 0 a removable discontinuity. So I'll point with an arrow. This is going to be a removable discontinuity, and -4 will be an infinite discontinuity. And number 6, it looks like we'll probably have the same thing happening where the bottom can be factored as x times the quantity of x plus 5, which means this x plus 5 and this x plus 5 can be canceled out, which means we have a removable discontinuity at -5. So at -5, we'll say that this one is removable. And at 0, it is going to be infinite. Infinite because the thing that was left over, namely this x, if you set that equals 0, you get x equals 0. All right, moving on. Over here, there's no problems. This is just a polynomial, so this one is continuous. In number 8, we have a fraction. Let's set that bottom equal to 0. If you do that, you'll see x squared plus 4 is equal to 0. Subtract 4, x squared is equal to -4, square root, and I get x is equal to the square root of a -4. You can't have a square root of a negative unless you use complex numbers, unless you use like imaginaries. So it is okay. It's impossible for this thing to be set equal to 0 is what I'm trying to say here. You can't take the square root of negatives, and therefore it's continuous everywhere. So we say that this one is also continuous. If the leftover isn't allowed to be set equal to 0, then it's continuous. And number 9, you can do all of these can be done with a pencil test, right? Didn't have to pick up my pencil, continuous. Didn't have to pick up my pencil, continuous. Number 9 is the same way. Didn't have to pick up my pencil, continuous. I know I did a not so good job of connecting those lines, but how would you tell this? You would plug in -1 to that x, and see what height you get. You get a height of 3, because that's where that spot is. You plug in -1 over here, and you get a height of -3, or sorry, positive 3. Yeah, positive 3, because -2 times -1 is 2, plus 1 is 3. Both of these have the same height, therefore it is continuous. Continuous. And number 10, it looks like we're going to have some leftovers. If we Factor that bottom is going to be x plus 3 and x minus 2. Notice that the plus 3's are going to cancel out, so that's going to be the removable discontinuity at -3, so I'm going to go ahead and label you removable. And then down here, this x equals 2 is going to be our infinite. And the rationale behind that is it's the leftover on the bottom. Leftovers on the bottom are always the infinite discontinuities. And number 11 is the first time that we don't have a graph. So now we have to do that algebraic interpretation that I've been doing from before. So let's go ahead and factor out the bottom. And if I do that, I get negative x squared over 4 times the quantity of x plus 4. I can't factor anything else other than the 4, and nothing here cancels out. So, okay, there's no removable discontinuity since I can't cross anything out. But maybe this thing can be set equal to 0, so I'm going to ignore you for a sec. I'm going to set you to 0 and see what happens. If I say 4x plus 16, I set you, the leftover, equal to 0, then I'm going to subtract 16, 4x is equal to negative 16, divided by 4, and x is equal to negative 4. Ooh, I found a value. This value, the leftover, will make an infinite discontinuity, so we'll say infinite. If this was like a square root of a negative or something weird like that, then it would be continuous. But it's not. It's a number, so it's infinite. All right, over here, it looks like we have some factoring to do in the denominator. So let me rewrite you as x minus 4. There's a negative out front. And then this is going to be the quantity of x. What times what is it? 2 and 4. So it's going to be x minus 4, x minus 2. And from there, you can say, oh, yeah, these two cancel out. And therefore, that's our removable at 4. Why 4 not negative 4? Because you're setting this equal to 0. X minus 4. If you set that equal to 0, then you add 4, and you get x is equal to 4. That is our removable discontinuity because these are both canceled out. That's what it says in our notes. So this is going to be removable. Movable. And what about x equals 2? X equals 2 is going to be their leftover, and we're just going to set that equal to 0. X minus 2 set equal to 0. This is our leftover section. And if I add 2 to both sides, I get x is equal to 2, and therefore that is our infinite. This one is our infinite discontinuity. Moving on to number 13, piecewise function. Just make sure that the left side and right side are the same. And there's not even an x for us to manipulate this. There's no way that these two are ever going to be the same. So this one is going to be discontinuous. But why? So let me go ahead and explain this one with a graph, which is probably the only way that I'm able to explain this. Notice that this is of that form that's very similar to number 1, a not equal to and equal to. So let's do the not equal to because there's only one spot that's 1. When I do that graph, let's go ahead and graph 3. So there's going to be 1, 2, 3, and I'm going to graph this line right here. Joink. Please, there it goes. So that's the graph of y equals 3 right here. And I'll also graph y equals 2, which is going to be at just this one. At 1, so this is saying at this suspect point at 1, so where are we on this line? We're at a height of 2, so I'm going to graph this point right here, this height of 2. And it says, hey, when I'm at 1, I am at 2. So what I have to do here is I have to come to my eraser and I have to go to my precision eraser and say, okay, I'm going to erase you and say, we really have a big point here, and then as I get closer and closer to that point, I'm in 3. So this is the graph of what's really happening. And just make sure that this makes sense. When I'm not 1, when I'm not this 1 point, ignore that 1 point. When I'm ignoring that point, I have a height of 3. Seems good so far. But when I am at 1, when I am at this point, I have a height of 2. And there it is. Everything makes sense. And now describe what's going on with this function. Well, I have removed it. You might say it's a jump because you jump down here and you jump back up. A jump discontinuity is reserved for the name when you glue pieces together that don't match up. These two pieces, the left and right piece, are glued together at the right point. The only problem is we've removed this point. We happen to put it somewhere else. It doesn't matter if you moved it somewhere else. We removed it. This is a removable discontinuity. Movable discontinuity. In number 14, I'm going to go, ooh, I've made a mistake on this one. I think, yeah, you can't do this. Let me talk about the mistake. I think what maybe I meant to say here was x minus 2, but then the answers on the back still don't make sense. Because watch what happens with the bottom. When I factor the bottom, it's going to be x plus 2 and x minus 2. And then I was hoping that one thing would cancel out, like x minus 2 and x minus 2. But that didn't happen. This is just a bad problem. In theory, if this was a minus 2, then you cross those off, and there's a removable discontinuity at positive 2. Why positive 2 and not negative 2? Again, the rationale is you set it equal to 0. The thing that we crossed out, x minus 2, That's what we cross off in the numerator and denominator. If you set that equal to 0, then you solve by adding 2 to both sides, and x is equal to 2, which means the thing that is crossed out is a removable discontinuity. You can say that this one is removable. But that isn't the case because this was a 4 up here. I made a mistake, or my program rather made a mistake. And the thing that would be a leftover, the thing that was not crossed off, x minus 2 here and here was crossed off. The leftover is x plus 2. If I set the leftover, I'll label this leftover. If the leftover x plus 2 is set equal to 0, then I subtract 2, and x equals -2 is our leftover or our infinite discontinuity, but that isn't the case because this was a bad problem. So I fixed it and solved it, but if you're doing this homework and you're watching this video now, just cross this one off. Sorry, I made a mistake. Maybe I'll fix it in future years and I'll actually put a 2 up there. And number 15, this one is the correct way of doing number 14, actually. So this one is going to be factored as x plus 2, nothing happens at the top, but the bottom is going to be x plus 2 and x minus 2, and now you can do the exact same process as before. Notice that these are going to be crossed off. That's going to be our -2. I'm not going to go through the whole logic of setting that equal to 0 again. That's the crossed off one, so this one is going to be removable. Anytime that you cross off things in the numerator and denominator, that's always a removable discontinuity, unless the same point happens with an infinite discontinuity. So I'll maybe explain that at a future date. Let me explain it right now. What if I had changed the problem to x plus 2 all over x plus 2, x plus 2? Then there's only one discontinuity, and that's at x equals -2. And the question is, what type of discontinuity is this without looking at a graph? And the answer is, well, it seems like it's both. You cross it off and it's a leftover. So who wins? Is it the removable that's crossed off, or is it the leftover? And the answer is, the one that has the power of infinity is more powerful. This one is a infinite discontinuity, so therefore it wins. It is an infinite discontinuity in this case. That is not number 15. It's a new problem that I've made up. All right, and let's go ahead and talk about this problem, which is a different problem. This is an entirely different point than this one. This is a +2 if I set it equal to 0. Therefore, this is an infinite discontinuity. I'll say this one is infinite. And what about number 16? This is just a polynomial. There's no bad things happening here. This is just continuous. There has to be like a fraction or bad things happening, or piecewise for things to go bad. There's nothing that can go bad in number 16. Number 17, it's a piecewise function. We just need to make sure that this height and this height match if we plug in our suspect point into each of these x's. So let's do that. I'm going to say this is -0 squared plus 4 times 0 minus 4. Let's see what height it is. Hopefully it's a height of 1, because then it's continuous. If it's not, it's discontinuous. So I get 0 plus 0 minus 4, which is just -4. All right, notice that -1 and -4, they are not the same thing. So I'll say these two numbers right here, not the same. Therefore, when you're gluing the left piece, this is the left piece, this is the right piece, the left piece went here, the right piece went here, they don't match up. This is a jump discontinuity. Jump discontinuity at x equals 0. In number 18, again, we're probably going to have to be factoring. The numerator is going to stay x minus 4. I have a negative out front. The bottom, I can factor out x, leaving me with x minus 4. And notice what we can do. We can cross off the x minus 4, cross off the x minus 4, which means at 4, the kind of the reverse of this, the opposite of -4, because we set it equal to 0, and solve. That is going to be our removable discontinuity. So this is going to be removable. And the thing that's left over, namely this x, set it equal to 0, and look, they did that. X is equal to 0, and that means that this is going to be our infinite discontinuity. Perfect. And number 19, what's going on here? We have -3, we have some weird fractions going on, but there's no bad things that are happening. Look, am I divided? Are there any x's in the bottoms? No, like this is just a polynomial. This is continuous everywhere. Continuous. If I had some sort of variable in the bottom, then I might need to check, but like literally plug in -3 and you're just going to get out an answer. Nothing bad is going to happen. If I plug in -3, just for what it's worth, it's going to be negative, I should write this down, -3 quantity squared over 2 plus -3 plus 3/2, and that's going to be -3 squared is 9 halves. But don't forget the negative that was originally up front. And this is going to be plus 3/2. So let's go ahead and combine these two really quickly. They have the like denominators, 2 and 2. So I'm going to do -9 plus 3 is a -6 and -6. So I'll go ahead and write this up here so you're not just following my verbal logic. I have a -6 over 2 now, minus 3. And that's going to be -3 minus 3, which is a -6. You just get a number, which isn't the answer. It's okay. You get a height. There's nothing bad happening there. There's no left and right piece that don't match. There's no removable discontinuity. There's no infinity that's created by having an x in the bottom. Nothing bad happens. It's just a polynomial. Polynomials are always continuous everywhere. Number 20 does have bad things happening. Look, there's an x in the bottom. So let's go ahead and factor the bottom. It's going to be x over x minus 4 and another x minus 4. If you're not comfortable factoring things really quickly without a Ninja Star, I can give you a worksheet so you can get better and better at that. Notice that there's nothing canceling out, which means there's no removable discontinuity. There's only these leftovers, which happen to be the same leftover. They're the same copy of 4. So leftovers are always infinite discontinuities. Infinite discontinuity. And I believe that concludes the homework. There are the solutions. I know that number, what was it? Number 14 got all messed up. So where is you for number 14? Yeah, it's saying that infinite discontinuities on both of them. That's not true either. Yeah, number 14, just ignore. Everything else I think was correct. Thanks for watching. I'll see you guys later.